Hi, everyone. So thanks to Nick for the introduction around what we're here to do today. And what I wanted to do is really just provide a bit of an insight into what we're up to in terms of Meta around the concept of AI training clusters and the challenges we're running into. And of course, what the opportunities are, because that's really what we're here to do today, is to understand what are the opportunities for these kinds of new technologies to be able to push us forward as we move through this next phase of technical development. So I just want to, right at the start, say thank you to a couple of people. This is Devatsa and Whitney. A lot of the information I'm going to be using today is from a paper and some talks that they've spent a lot of time working on. So thank you to them for that. And the slides I assume are going to be going out, and I'll make sure that people have links to these, the paper and the talk. So what am I going to walk through today? I want to explain the growth we're seeing in AI training and what that looks like in terms of model growth. How we've addressed that with the training systems we have today, what the upcoming challenges are we see, and how we feel that hardware software co-design in this kind of open programmable infrastructure space can help that. And then finally, I have a bit of a directional, I wouldn't call it a call to action, but a directional piece of information about how we tend to interact with this type of technology and how we can really see the community making those barriers as small as possible. And that's very important to us because I'll talk about why that is at the end and then just finish off with a summary. So, and how do you guys want to do questions? I guess questions at the end. So I'll kind of push through and then please pop up with any questions as we finish off. So first up, model growth. The complexity of the models we're dealing with, as well as their size, is currently one of the key fundamental infrastructure issues we see. And there are a few very important points to get across to you folks as the audience here today. One, recommendation models are different. So obviously we spend a lot of our time working on how to ensure that recommendation models work very well, that they tie in with the best recommendations they can, and that they are as successful as possible. They pressure hardware, and which is what we'll work on, in very different ways to most traditional AI workloads. As you can see, DLRM, which is a sort of public example of a deep learning recommendation model, if you actually look at the amount of petaflops it requires, the amount of compute, it's relatively low when compared to some of the sort of GPT-3, these kinds of models, which are very, very high and very, very compute intensive. But in terms of parameters, it's actually up there right at the top in terms of the amount of parameters we require for these models. And that is very important to our infrastructure because it means that our memory, speed, and capacity are vital really to our performance. And the second part of this is it means that the size requires us to focus on synchronous training across many, many different nodes. And that's important because that synchronicity means that we need to have sort of very specific fabrics to be able to tie all these systems together. And we'll talk about that a little bit more as we go along. So this is the problem space we saw today. This is, in fact, this is probably the problem space we saw a couple of years ago, which has led to the training systems we have today. So what does our current synchronous AI training architecture look like? Because asynchronous updates lead to a degraded model accuracy as the scale increases. So you can think about it. If you've got a bunch of different components all updating a central parameter server, which has got the sort of the golden version of the model, and you start extending it so you have more and more of these servers updating it, you're going to get more and more noise in those updates. And that means that we had to move towards a synchronous AI training architecture as the models increase in size. And that meant that we had to utilize really low latency transport. So we need low latency transport with direct data placement, really. And why is that? Because if you look at I'll get to this in the next slide, but if you look at our overall system design, we're actually trying to place data directly into accelerators rather than move it through a number of chips along the way, terminate the transport somewhere, copy data across. We don't have, frankly, the PCI lanes or the connectivity for that. And that's very important. And with that, it means that we need transport that can really terminate at the endpoint networking device. Now, an example of that is Rocky. This could be RDMA, InfiniBand, if you remember Omnipath, anything that really terminates at the networking device. Now, the last point here that we have is around the sort of ease of scaling. So there've been many papers in the past. I remember Microsoft published one a bunch of years ago around how to integrate RDMA Rocky networks over their front-end fabric and tie things together. What we've decided to do is, just for the ease of scaling and management, we actually have a separate back-end network that services our RDMA Rocky networks. Would help if I did click onto the next slide. Boom, there we go. So what is that node? So if you click onto the previous slide, you saw this Xeon X node. This is the, if I can call it, the box that really contains all of the compute. So what does it look like in there at the moment? This system really ensures that we have an ease of data placement by having RDMA NICs, which are terminating the transport, directly attached to the same root complex as accelerators. This means we can basically set up buffers which are pointing to memory in the accelerators and dump data directly into those accelerators. And that avoids a bunch of memory copies, a bunch of other stuff we need to do. The accelerators also have a high bandwidth network in between them inside the box. And the reason for that is, if we go back to the previous one, we have to service these all reduced collectives, which is effectively a block of data which just gets reduced upon by all of the nodes inside the box and outside the box. And that means that by having a high bandwidth network inside the box, we're able to significantly improve the overall performance of the system. And that's very important. And there's also, we've kind of focused on the, if I can call it, the back end of the box here, but there's actually this ingest as well. I don't know if people remember a phrase that was used a lot, maybe 10, 15 years ago, around storage systems, around feeding the beast. This is when, if you remember, the CPUs were scaling like this, and storage networks were struggling. So really what we're doing here is the next generation of that, but we have to actually make sure we can ingest data at a high enough rate to be able to service the accelerators which are sitting in these boxes. And this is again where the CPU is very important, because really at the moment this system is focused on ingest. So we basically pull in data from the outside world, and then we have to DMA it across into these accelerators. And that's where the rest of the system, which sits here at the front, is really focused. And then there's one last part to this whole system, and that's the ingest part. Now, this consists of a number of things. One, storage. Of course, all of these model parameters, all of this information we have needs to be stored somewhere. If it isn't, then we're going to run into trouble. We have a multi-layered distributed storage infrastructure, which has been explained in other papers. There's some in the reference I put in the slides already. And there's many more papers out there, which actually that paper references to, which you can go if you want to understand more details about the storage infrastructure. But effectively, this is a multi-layer distributed storage. Now, the key thing is that the data which comes out of that storage, that data is not in the right format to be processed directly. It needs to get normalized, linearized, and there's a few other things that need to happen to that data. And so then there's a pre-processing step. Now that really that lightweight pre-processing gets done by a distributed set of small, we call them readers, but really these are small hosts, small standard compute hosts. And they then push that data onto the training compute, which is the Xilinx box, which then takes that data, ingests it, pushes it into the accelerators, and once all the accelerators have the right data, then they can all basically do the actual training job, run through it, and then update the system as they go along. And that's really what the architecture looks like today. So what are the upcoming challenges we see on this? This is obviously where we are today, but that's not the end state. There's a few new challenges we're running into today. There's a few new things which we're going to hit, and we have to really start looking at those. And this is where the opportunities are. So, problem number one, power. Our current trajectory, if we look at the way that power is scaling in these systems and the way that these models are scaling at the moment, the power trajectory is not sustainable. We need to work out ways that we can flatten the curve. And for that, we will need model optimization, but not only model optimization. We will also need more and more hardware optimization. And this is really where hardware software co-design comes in. We need to have a tight understanding of the infrastructure while maintaining the ability to have flexibility to software engineers, which sit higher up in the stack. We can't have a world where, effectively it takes 6 months to iterate, test out new models, update new things, try things out. That's not the way that we can create scalable innovation for those who sit above us as sort of low-level engineers in the stack. And that's very important. So we need to make sure that we actually leverage the ability to design the hardware and software in parallel in conjunction with each other and tie in that development environment with the end user. And this is really important. I'll talk about this a little bit more later on, but I think one of the key things for us is that any kind of infrastructure in this space needs to think very, very, very carefully about how it integrates to the workflows that developers have today. It's all well and good coming up with new workflows which are optimal for your hardware, but a lot of times, not always, but a lot of times that may not be the best way to go. The best way to go may well be to understand what the workflows are that are used today, and then underneath the hood, work out how you can actually tie in your hardware with those workflows. I can talk about that a little bit more as we go along in the Q&A as well. So what are these opportunities we see? Talking about it at a high level, big problem, power scaling right now, we can't go on like that. What are the opportunities we see specifically? One, in the ingest pipeline. So the first problem we're seeing is if you look at the supporting services deployment power versus the actual training cluster deployment power, we see some scenarios where potentially the supporting services may end up, if we do nothing and we just carry on as we are, may actually take more of the cluster deployment power than the actual training clusters do. That's of course not a scenario we want to get to. This means that we need to really focus on how we can optimize the storage architecture and leverage new technology. I used the example of network attached storage here. So we can really push this trend down. There's a number of factors contributing to this. And one of the other ones that's really important as well as that data pre-processing I told you about earlier, where you're kind of doing some very simple normalization, some very simple pieces of compute. But because of the nature of that compute, it's very stream focused. It requires, a lot of hardware at the moment to be able to handle it. And so looking at things that we can do to improve that is going to be very, very important. And this is the first area where there's potentially some gaps here that can get optimized over the next, let's say, 5 to 10 year time horizon. And this is something which I would encourage people to think about and really look at. Second area where you can potentially have some optimizations. So this is really the backend network communication. So as cluster sizes increase, this is not, I don't think this is going to shock anyone, but as cluster sizes increase, more and more of the overall scaling performance is really driven by communication. So if you look at this chart here, apologies for not having any real numbers on the bottom here, but as the cluster sizes increase, the communication becomes more and more and more dominant in terms of the overall performance of the training job. And that's really, really important. And this means that we really need to focus on how do we improve loss resiliency or losslessness. So I'm getting a little bit more into the weeds. As a lot of you understand, things like RDMA really rely on lossless transport. If you look at things like, IP, that there's a whole mechanism which ties around the system to ensure that. If you look at the way that Rocky works, it really relies on a combination of PFC, ECN. There's the DCQCN paper, which the folks from, I think it was MIT and Microsoft worked on together, which was really interesting. And there's a few other examples like that as well of people who really focused on that sort of losslessness of the network. Another way to go is also loss resiliency. This is, of course, if you think about TCP, that this is the way that the 99.9% of the world works. However, of course, there's some issues there with tail latency. So if you can work out ways to bound latency while having loss resiliency, it gives you a lot of power. This is all publicly known that there are some topologies that maybe don't work well with losslessness as the way they set up today. So having loss resiliency could potentially enable new topologies, new ways of doing things. And that's really important. The second one, link utilization. So there are some cases where you can look at systems and you may not have enough, let's say, active connections or entropy in your link queues. And that's something which is very important for us long term. So working on ways that we can improve our overall link utilization in the network will be something which can potentially help us a lot in terms of performance. And then the last one I mentioned here is direct data placement, of course. Now, this is something we already have, but there's potentially ways that we can improve how this works in terms of how we allocate memory, how we DMA data to the right place at the right time, and how we perform in terms of, let's say, registering memory regions, things like that. These kinds of areas can provide some really interesting long-term benefits to us, and are really things that we would encourage the industry as well as ourselves to really think about over the next 5 to 10 years. So coming up to close to the end of my little talk, and I just wanted to bring up one more thing, which is how we see open programmable infrastructure working with the rest of the stack. So, and this is very important. Really, from our point of view, ease of integration with existing open source software will make adoption much easier. It will make testing much easier. It will give us the ability to much more quickly validate technology. And this is one of the big problems, I would say that we as a community have to think about. And I can, talk about my experiences in my previous life. I was at a sort of small company that was doing network processes. And one of the biggest challenges was just getting technology getting it into a state where people can very quickly get it up with whatever Linux distribution they have, whatever set of tools they have, whatever this, whatever that they have, that bring up process and getting from, okay, here's a card, here's an accelerator, okay, plug the thing in, now what? Getting from that to running traffic, to running workloads on that accelerator, keeping that time short will significantly, I think, improve the ability of this technology to get itself to market. And that, I think, is one thing which I'd really encourage folks to think about over the next couple of days. How can we tie this technology to what's happening in the rest of the world? And that's, obviously why what Rob and Nick and team here are doing is awesome, is because they're bringing this concept in and they're really starting these discussions. And I'm very, very grateful for them to do that, because without that, we're all going to stay in our own little space and we're not going to work together. So I'm very excited about that piece. The second part here is how you tie that into sort of upstream systems. I'd encourage people to upstream drivers and really think about how you integrate any special features you have with upstream technology as it is today, or there are cases where that won't work, how you build that in and how you contribute that to the community. That tends to make that process much smoother than we've otherwise seen. And then the last thing here is monitoring. This is another challenge which we run into a lot, and I think a lot of other people run into. I think there are definitely a bunch of areas where standardized, potentially counters, and potentially as these things get more programmable, of course, trace points will really add some clear value. And that's something to think about a lot, because this is, again, one of the challenges you run into as you start scaling and scaling and scaling. Getting a wider understanding of exactly what certain counters mean, what certain trace points do, will potentially provide a lot of benefit to the overall community. Now, of course, not all of this stuff can be standardized, because then it wouldn't be your open programmable hardware, it would be something else. But I think where it can, it would be very useful to strive for that. And I think those are really the key messages that I wanted to get across for people to think about as we go along over the next 2 days. Is one, how do we make the tool chains easy to use, reuse as much as we can? How do we integrate this with kernel drivers and other offloads that already exist? And three, how do we make it so that the users can monitor this technology and understand what is going on? I think those are really the three key things. Then I have just if I can get to it, just have a quick summary. One, in terms of meta, we're focused on synchronized training as well. This has been shown to scale to recommendation models with trillions of parameters. It requires low latency transport, and we need to have that direct data placement really to be effective at the moment. And what that direct data placement means is likely it means transport termination at the endpoint. But of course, potentially you could do something like keep the transport on the CPU, copy headers across, and then copy data across to the accelerator. There are other ways to solve these problems. And that's why I call it direct data placement rather than sort of hardware transport, because there are ways that you could potentially get around this without it actually being hardware transport. So that's the first important thing. Second, really, as this stuff is scaling over the next 5 years, we're going to need hardware, software co-design to actually be successful. I know there's been other public articles. I remember there was one in the ACM a few months ago from a large cloud provider, really talking about how important this hardware software co-design process is to move forward over the next 5 years of the business. And I think the same thing is applicable to us. And finally, it's essential that we integrate this hardware as much as we can with standard open source tools. And that, I think, is really the last key thing I wanted to get across. That process is what gives us the flexibility, and it decreases the friction to actually adopt this technology. And that's something I'd love to get across to you folks to think about in the next couple of days. Now, I think that's really all I had. So I think we've got a bit of time. So I think we can open up the floor to some questions and people can ping them at me.
Thanks, Nick. We've got a couple questions that have come in. Please, everyone, use the chat window to type in your questions and I'll read them off. So the first one is, do you see CXL as an accelerator performance enabler?
As an accelerator performance enabler? That's a really good question. So I mean, there are different parts to CXL. If you look at something like CXL cache, purely from a very selfish networking standpoint, I can see that being something which is very interesting to enable transport acceleration. Because like if you're something like a TCP state table, you can potentially offload some of your TCP state table onto your device, and potentially even run something like TCP on the device for limited cases, and then throw exceptions up to the host. That's the one thing. If you look at things like CXL mem, I think there's been lots of discussion about how CXL mem can enable accelerators to have more memory, for example, by having access to a wider pool of memory. And that is obviously something which is important in some use cases. So as I said, we have at least in AI training, you can see there are cases where we need to have a lot more memory than we have available today, and we need to have that at high bandwidth. So yes, I do see CXL as something which maybe not in the AI training use case, but in potentially other adjacent use cases can be very useful.
Great. Next question. Thank you for your talk. Can you talk at all about how you or Meta think about balancing scale up, meaning local to the box, versus scale out interbox computing? As far as I can tell, the balance really depends on the size of the job, the number of parameters, etc.
So I probably can't go into too much guts, but what I can say is this. We will keep things on the box if we can, but fundamentally the training models are so large that they cannot stay on the box. They have to go across the network. And of course, we'll do as much in-box communication as we can. And there are collective communication algorithms out there. You can look at, Nickel, UCC. There's a couple of others. I mean, the UCX stuff, which is now titled with UCC. There's a bunch of good collective communication libraries out there that really handle this stuff. And again, this is where the whole thing about looking at what's happening out in open source is really important, because a lot of these tools get reused everywhere.
Great. Hi, Nick. Do you see infrastructure evolving in two directions, one for AI and one more for the rest of the applications? As we do software and hardware co-design and optimizations, do you see it going in two different directions?
Hey, how are you?
That's a very good question. I think probably the right way to think about it is something like, how car technology develops. You get a lot of stuff that starts in like Formula One cars, but eventually it's going to end up in, your, car that you drive around the city. Especially things like safety features, especially a lot of things around efficiency. So I don't really see them going in two directions. I see one driving innovation which gets reused in the other. But there are also innovations which are viable in the wider network, which may not be needed for that. So it's not like, if it's a bunch of Venn diagrams, it's kind of like this. There will be a lot of overlap, but it's not going to be 100%. So.
Okay, what capabilities is Meta looking for apart from RDMA for DPUs or IPUs?
So we're definitely looking at and exploring a lot of features and functionalities. RDMA is certainly not the only one, and it may be that, and also I don't see RDMA as a, by the way, to the speaker, I don't see RDMA as a uniform thing. RDMA is a combination of features which allow you to do, basically move data directly into accelerators in that case. That's really what we use it for. And does that mean that, you need to hold by spec ABC? Maybe, maybe not. There's a lot of room for innovation within that, within IPUs and DPUs. It's not that it's one, it's not that it's sort of, here's the feature, tape out the feature, done, boom, that's it. No, there needs to be flexibility, there needs to be programmability. I think that's very important. Now, beyond that, I think the one I mentioned is the sort of pre-processing one. That's something which potentially you could work out how you can offload that to a device. That tends to be sort of a streaming optimized workload. So there's definitely some stuff there that could be very interesting. I can also see potentially integrating it with other kinds of accelerators as well, where you don't really have RDMA, but really you're dealing with sort of streaming type transactions, where it's just moving through the device. And then I can think of other couple, but I think that's enough for now.
Thank you. Do you see a petabyte parameter scale training happening soon? What do you think the challenges would be?
I am not the right person to answer that question. So I will defer that one.
All right. Your slides imply a heavy power cost for the tasks of services and communications as cluster size increases. What sorts of services or communication tasks are particularly power hungry today for you?
Sorry, you broke up there for a second. Go ahead.
Okay, I'll start over. Your slides imply a heavy power cost for the tasks of services and communications as cluster size increases. What sorts of services or communication tasks are particularly power hungry today for you?
So I think that in terms of tasks that are power hungry, I mean, it is fundamentally the ones I mentioned, which is actually getting the data from storage and the ingest pre-processing. Those are the power hungry tasks on the front end. On the back end, the power hungry tasks are one. We actually have to build out, these very high throughput fabrics. So fundamentally, everything from SerDes up is cost there. And then of course, beyond the network, you've obviously got the compute as well, which is, accelerators tend to be pretty heavyweight here. So on the training cluster side, I would say it's network compute. And then on the other side, on the ingest side, I would say it's, really getting the data out of storage in the right format, which ties in with the pre-processing and how we do storage.
Thank you. I think this is our last one here. Nick, although if somebody has more questions, please bring them in. Nick, if you could have one new tool to help you in your work, what would it be?
It's a really good question. That is a really good question, Chris. What would if I could have anything in the world? Well, there's a lot of things I want. Probably, I think the biggest thing right now on my end is really not one tool, but it's the combination of tools. So it's getting hardware, and this is kind of what I'm talking about when I'm talking about that stack. It's about being able to get hardware and very, very quickly get it into running at least test workloads in the lab. And to do that, really making sure we have those barriers as small as possible is the most important thing. And that means basically good open source software. That's really the thing I'm driving for there in terms of compilers, in terms of generally the tool chains, in terms of monitoring, debugging infrastructure, and also in terms of device drivers. That, frankly, that's actually the area, that sort of low-level software is actually the area where I think a lot of times we hit challenges. And that's what I would encourage everybody on this call to really focus on, is making sure those tools are as good as the hardware.
Thank you. Okay, we have one last question. How large is the impact of vendors failing to upstream drivers or upstream them in a timely manner?
I don't think it's not easy to quantify that. I can't say, it's X big, but it will make life harder. If your tool is, let's say your hardware is 1,000,000 times better than anything else out there, sure, these are barriers we may overcome. But if your hardware is 50% better, maybe 100% better than whatever else is out there, then even in those cases, you may still, it's gonna be more of a barrier to entry. So I would say it's a barrier. Doesn't mean that nothing would ever happen. But it does mean that it's harder to test things, it's harder to validate things, and it's also harder to eventually bring things into production. And that's really the key message there. So basically, there is a significant impact, and I would encourage everybody to do this, to upstream their drivers in a timely manner.
Well, thank you, Nick. This has been very illuminating.